Okay, so here we are, Chapter 8, Electron Configuration and Chemical Periodicity. And the first thing that we're going to look at in here stems from Chapter 8, and that we learned what are the first three quantum numbers. So we talked about these quantum numbers N, L, and ML, okay? And we learned about those, and I'm going to go over those a little bit more today. I have some information about those in a slide coming up. But right now, in a few minutes, we're going to talk about a new quantum number, a fourth quantum number that doesn't come from the Schrodinger equation, and it's called MS, okay? And before I get to that, while I really have all of your attention, the first thing I want to tell you is this, okay? It's on my next slide, and it just shows a periodic table. And what we're going to be dealing with today are electron configurations. Okay, and what I need you to know is that the first two groups or families of the periodic table, we call that the S block, and I want you to memorize this. Groups 3A, so that would be, let's see, that would be groups 1A, and 2A. Anyhow, it doesn't matter. And then from groups 3A to 8A, so groups 3A to 8A, and of course they have the other numbering system here. Groups 3A to 8A, we call that the P block. I'm just going to clean this up. 8A. We call that the P block. Where the transition metals are, we call that the D block. Okay, so the D block, and then the block with the lanthanides and actinides, we call that the F block. And you remember that we talked about angular momentum quantum number, and we talked about L values, and that we said that when L is equal to 0, 1, 2, and 3, that I would have an S orbital or a P orbital or a D orbital or an F orbital. And we even looked at the shapes of those. We said that the S orbital looks like a sphere, the P orbital looks like a dumbbell, the D orbital had some interesting shapes, and the F orbitals were even more interesting than those. But what I really need you to know from this slide is where the S block is. So you need to know where the S block is. It's over here. Over here is the P block. Down here is the D block. Down here is the F block. And you need to know which angular momentum quantum number represents S, P, D, and F. All right, so that's the first thing I want to tell you. And I remember learning this in high school way back in the early 90s. And that was the first thing that my teacher told me, and I never forgot it. And I think it's one of the easiest ways to learn electron configurations. Now, let's get into that fourth quantum number. So the fourth quantum number, again, we already talked about the first three quantum numbers, which are N, L, and ML, but now we need a fourth quantum number, and that fourth quantum number is called MS, and that represents electron spin, okay? So we could just call that, electron spin, or you could call that the spin quantum number. It's probably called a few different things. But where that number comes from, okay, is if you think about an electron as being a small body with a negative charge, it says here that if you take a small body, or any body really, if you take a spinning charge, okay, and you spin it around an axis, what's going to happen is when you have a charge that's spinning around, it's going to create a little magnetic field. Now, if you think about the directions in which the electron can spin, now it might be counterintuitive, but it can only spin in two directions, okay? So it can only spin with the axis pointing up like this, or with the axis pointing down like this. And you might be thinking, well, couldn't it, spin in an infinite number of directions? No, you're going to have to take my word for it that it spins in only these two directions. And we call these by convention plus a half, and then we call this one minus a half, like this. And if you're like, where does this come from? Well, I'm going to talk about it more in a second, but you see here, minus a half and plus a half. And what happens is if you take a beam of electrons that have one or more, a beam of atoms that have one or more unpaired electrons, and you pass it through a non-uniform magnetic field, it's going to split into two beams. And what that basically tells you is that some of the electrons are aligning with the magnetic field, and some of them are aligning against the magnetic field. And if you're wondering, are you going to ask me all about magnetic fields and everything? No, I think the only thing you really need to know from this slide is that an electron can either be plus a half or minus a half, which is the possible MS values that, again, are shown right here. And I think you should also know that a spinning charge is going to create a magnetic field. So I can underline that for you, or highlight a spinning charge will create a little tiny magnetic field. And if you take organic chemistry with me in the future, we'll talk about electron spin even more in that class. So anyhow, a little bit more about that fourth quantum number. It's electron spin, so that's what we're going to call it. MS will be electron spin, okay? And then we label that, and I'm repeating myself, but I want to make sure you know it. We label it MS like that, and we have two possible values. So we can have MS, excuse me, is equal to plus a half, or MS is equal to minus a half, okay? Like that. And that's going to be our fourth quantum number. And again, that fourth quantum number doesn't come from the Schrodinger equation, right? The first three quantum numbers did come from the Schrodinger equation. And if you're like, you know what, I had a long weekend, my dog ate my computer or something, and I forget what the first three quantum numbers are. Well, here they are right here, okay? So we covered these in chapter 7. The first one was N, the principal quantum number. It only has positive integers, so 1, 2, 3, 4, 5, 6, 7. And that represents the orbital energy, or even easier would be the orbital size. And the bigger the positive integer is, the bigger the size of the orbital, you can imagine. The next one is L, which is the angular momentum quantum number. If you're the kind of student who likes to poke around the internet and look at videos, that other people put up, which I recommend, okay? I highly recommend that. Sometimes they call the angular momentum quantum number. Sometimes it's called the azimuthal quantum number. I don't think our book uses that word. Anyhow, it goes from 0 all the way up to n-1, and it corresponds to S, P, D, and F. And what does that correspond to? It corresponds to the shape of the orbital. The next one is ML, which is the magnetic quantum number. That corresponds to the orbital orientation, and that can have values of L up to 0, up to plus L, and then finally the last one is the one we went over now, is MS, and that represents the direction of electron spin, okay? So sometimes, and even today, we're going to look at lists of quantum numbers for electrons, and we'll always, order them like this. We'll always have N, L, ML, and MS, like that. We'll always put them in order like that. Okay, there we go. So something else, for the people who are still paying attention, and I hope you all are, something else that I'll just, kind of put this bug in your ear maybe about electron spin is, I'll just write this in here. Each orbital, so when we talk about orbitals, so each orbital can hold a maximum of 2 electrons, okay? I don't know why I put the negative symbol if I'm writing the whole word out. Anyhow, each orbital can hold a maximum of 2 electrons, all right? And so that is something that we call the Pauli exclusion principle. So it says here, no 2 electrons in the same atom may have the same set of 4 quantum numbers. Now remember, the 4 quantum numbers, and I'm going over this again, are what? N, L, ML, and MS. And so what our goal is today is to take any element on the periodic table and to be able to provide a set of 4 quantum numbers literally for any electron in any atom. And if you're like, well, what about an element like tin? Okay, so tin has 50 protons, 50 electrons. You mean I could write a set of quantum numbers for, say, the 33rd electron? Yes, absolutely you could. What about an element like mercury? That's got 80 electrons. Wow, could I write one out for the 74th? Sure. Choose your number, okay? That's part of our goal today. Okay, and again, that Pauli exclusion principle says that 2 electrons can occupy an orbital, but they're going to have different spins, right? One will be plus a half, and one will be minus a half. So MS can equal plus a half or minus a half, like that. The spins of the 2 electrons in the orbital will be opposite to each other. So again, plus and minus, those are opposites. So not really a bone-crushing, complicated concept there, I don't think. Anyhow, let's move on and kind of switch gears a little bit, tiny bit. I want to talk about 2 things here for a few minutes, just to kind of rationalize what affects atomic orbital energies, because we're going to talk about atomic orbitals a lot today. We're going to talk about the relative energies, and there's two kind of major things that affect the energies of atomic orbitals. The first one is nuclear charge, and the second one would be shielding by other electrons. And there's a couple of types of shielding. And it says here, a higher nuclear charge increases the nucleus electron interactions and lowers the sublevel energy. Do you guys remember earlier on in this class, I taught you about this right here, effective nuclear charge? And I said that the more that the outer electrons feel of the nucleus, the more attracted to the nucleus they're going to be, right? So that's more of the effective nuclear charge they feel, or the charge of the nucleus that's having an effect on them, right? So it says here that, again, a higher nuclear charge increases that nucleus electron interaction. Okay, it's going to lower the sublevel energy. Good. So basically, stronger interaction, lower energy. Okay, I'll repeat that. Stronger interaction, lower energy. Good. The shielding by other electrons, though, reduces the full charge to an effective nuclear charge. And I went over that with you before, but I'm going to talk about it a little bit again today as well. It says the effective nuclear charge is the nuclear charge that an electron actually experiences, right? If you take the nucleus of any atom, say it's a carbon atom, right? There's 6 protons in there, but do all of the electrons, do all of the 6 electrons in carbon, do they all feel the net effect of 6 full protons? And the answer is no, okay? And also, the orbital shape is also going to affect sublevel energy. So first, let's talk about that nuclear charge a little bit more here. And this might seem complex when you look at this picture here, but I'm going to distill it into the simplest possible bit for you. Now, it says here that it says the effective nuclear charge on sublevel energy. Okay, so it says a greater nuclear charge is going to lower the sublevel energy. So we have 0 kilojoules per mole, right? And as we go down this way, right, we're getting more and more stable, right? So it's getting more and more stable going in that direction. All right, so we got that much. All right, delete that line too. There we go. Okay, now it says we're starting out with a hydrogen atom right here. Okay, so we're starting out with a hydrogen atom. It has an effective nuclear charge of 1. Okay, or sorry, I should say it has a nuclear charge of 1, right? It has 1 proton, and then it has 1 electron out here. Okay, now it says this electron is easiest to remove. It says that this sublevel is least stable. Now, it's saying compared to what? Okay, if you compare it to a helium 1 plus ion, so think about it. And if you're like, what are you talking about, Mr. DM? Hold on. Helium. Where is helium found in the periodic table? It's element number 2. That means it's got 2 protons in the nucleus. But if I have helium plus 1, well, helium itself, if I have helium, it should have 2 electrons, right? 2 protons, 2 electrons. If I hit a helium plus, that means that it lost an electron. So that means that I have 1 electron on the outside, but now I've got double the amount of charge, right, in my nucleus. So that means it's going to stabilize it even more, because what did we say before? We said that the greater nuclear charge that the outer electrons feel, that means it's going to be harder, or sorry, it's going to be more stable, right? And if we take the same rationale and we look at a lithium cation, a lithium 2 plus cation, now we've got 1 outer electron and we've got 3 protons, okay? So what's the rationale here, or what's the take-home message? Like, what's all this, semicircles or whatever, okay? Or quarter circles, I should say. The idea here, the only concept that you need to really get from this slide is that as long as we have 1 electron on the outside, okay, as long as we have 1 electron in our atom or our ion, as the nuclear charge increases from 1 to 2 to 3, like that, it gets more and more stable. It gets more and more stable. Why? Because it's held in more tightly by that nucleus, okay, by that nuclear charge, greater nuclear charge. Okay, give me a thumbs up if you just follow me on the concept. Greater nuclear charge that the electron feels, it's more stable. And then moving on with life. Yeah, okay, that's nothing more than that. Now, okay, great. All right, thank you, guys. Good. It's always good to get feedback along the way. Okay, it says here now shielding and orbital energy. So this has to do with electrons and their effect on each other. And I'm going to try to go over this quickly because sometimes I like to ramble on about this a little bit. It's kind of a fun concept. But it says here, actually, there are 2 types of electron shielding. Okay, so 2 types of electron shielding. You can have electrons in the same energy level shielding each other a little bit, not much, but a little bit. But then you can have inner electrons, what we call inner electrons in inner energy levels, shielding the outer electrons really effectively. The farther from the nucleus an electron is, the lower the effective nuclear charge is going to be. Okay, so let's take, take a look here. A picture is worth 1,000 words. So the first side, this slide is kind of divided. It's not kind of, it is divided into two sides like this. On the left-hand side, what they're showing you is that electrons in the same level are going to lead to a slightly lower effective nuclear charge. And the way I would kind of describe this, to students is maybe, these two electrons are both fighting for this charge here. So they're going to shield each other a little bit, okay? And if you think, well, it kind of makes sense that another way you could put it is, okay, I have a 2+ charge, I have a 2+ charge here. Well, the 2+ charge on the top is kind of it's pulling this electron in and it's pulling this electron in. So the charge is kind of split, right? It's kind of going here and then it's going to the other one. Whereas if I remove one of these electrons, right, I go down here, okay, well, then this electron is going to be much harder to remove because it's got the whole entire 2+ charge to itself, okay? That one's a little trickier, but it's a lesser effect, right? It even says here, slightly lower effective nuclear charge. The concept on the right, I think, is much simpler to understand. It says here that electrons in an inner level or inner energy level lead to a much lower effective nuclear charge. So if we draw our attention to this electron right here that I have highlighted in green, well, it's feeling some of that 3+ charge from the nucleus, but you got two inner electrons that are like moving around, right? This is where it would be more fun if we were in the face-to-face classroom, but they're kind of like, and they're blocking this guy, right? They're shielding it. Another way that I've heard people explain it is like this, okay? Imagine you're at a movie theater, okay? Imagine you're at the movies. If you're at the movies and somebody comes sits in the row next to you, it doesn't really, block your view of the screen very much, okay? You're not worried, if somebody with a big, tall, hat sits in front of or sits beside you. But if somebody with a giant hat sits in front of you, well, that's going to block your view of the screen, okay? So what you should, and if you're like, what should I know from this slide, Mr. Dion? I would say the take-home message here is really that electrons in the same energy level are going to shield each other slightly, or they're going to block that effective nuclear charge slightly. But inner electrons are going to block the effective nuclear charge that the outer electrons feel quite a bit. Okay, quite a bit. Okay, it even says here much more. Okay, give me a thumbs up if you're with me on that, and then we can move on to more interesting stuff or something that I'll really quiz you about in a second, because I'm not going to ask you, Joshua, write me an essay, 3 pages all about effective nuclear charges. It's more just understanding what the heck is going on. So if you take an element like potassium, okay, let's say you take potassium. Potassium is element number 19 in the periodic table. So potassium is element number 19. If you think about the sublevels, okay, when you start at a 1s sublevel, and if you're wondering, like, where did you get these from, Mr. Dion, and how did you get this order? I'm gonna go there in a second. But what you need to know is as we go from a 1s to a 2s to a 2p to a 3s to a 3p to a 4s like that, we're getting further away from the nucleus. And what's the trend that we see over here for effective nuclear charge? Well, first, let's look at this number, 18.49. Remember, in a 1s sublevel, S has an angular momentum quantum number of 0, right? So that means it can only have one orbital and it can have a maximum of 2 electrons. So there's only 2 electrons in this sublevel, in the 1s sublevel. That means that they're both going to feel almost that full 19+ charge in the nucleus, right? They're going to feel almost all that, but look, they feel, I have a Band-Aid on my thumb, I split it open, so it's hard for me to make the screen bigger and smaller. Anyhow, it has a little less, okay, a little less of the effective nuclear charge. Why? Because we said that electrons that are in the same level, they shield each other a little bit, okay, but not much. But then as soon as you go to a 2s, right, you're getting to a bigger principal quantum number. Okay, electrons are further away from the nucleus. Look, they don't feel nearly as much. Okay, now this one here is an anomaly because it goes up a little bit. I think that's probably due to the shape of the orbital. But the idea is this: is as we go in this direction, right? As we go this direction, that the effective nuclear charge gets lower and lower and lower, right? It says here the outermost electron, the 4s, has a very low effective nuclear charge. It's only 3.5, and it's due to the shield of 18 inner electrons. And if you're like, well, where do those 18 inner electrons come from? We're going to get there in a few seconds. But what you really need to know is that inner electrons are going to block, or they're going to shield outer electrons from that nuclear charge. All right, well, let's keep going here. Here's another beautiful slide with that periodic table that I showed you. And not only do you have to know where the S, the P, the D, and the F blocks are in the periodic table, you should know that the order of these sublevel energies, okay, goes S is lowest, P is next, D, and then F is the highest, okay? But you're like, well, Mr. Dion, you already taught me last class. You said, you went over this probably 10 times. The L is equal to 0, 1, 2, and 3, and then we had them in that order anyway. Well, good, okay? But that's the order of sublevel energies. So what I'm saying is that as you go from a 1s to a 1s over here, and then you go to a 2s, and then you keep following, and then you have a 2p, okay? And then you have a 3s, and then you keep following. And if you're like, well, Mr. Dion, where are you getting these red lines that you're drawing from? Okay, look, all I'm doing is this. I'm just following the periodic table. I'm starting on element number 1, hydrogen. Then I go over to helium, like that. Okay, yes, it's a little bit of an anomaly that 1s is over here as well. We can talk about that more later. Then I'm going over here to element number 3, lithium. Okay, then I go over here to beryllium. Then I go over here to boron, carbon, nitrogen, oxygen, fluorine, right? Neon. Then I'm going to go back here again. Okay, are you following me? All I'm doing is walking across the periodic table. I'm going from 1 to 109, right? Okay, so 1 to 109 or 110 or however many elements there are now. Okay, good. All right, that's all we're doing. All right, and we're going to use this moving forward, okay? And something else I would like to remind you of is this, okay? Is that from now on, and I've told you this earlier on in this class, whenever I'm lecturing or whatever you're doing anything to do with this class at home, I want you to always have a periodic table in front of you. And I can do you one better. It should be one that you can write on, okay? One that you can scribble on with a pencil and mess around with, because that's going to be very helpful. Now, again, if I just kind of summarize what I had written here, it says each energy level is split into sublevels of differing energy. Splitting is caused by penetration and its effect on shielding. I'm not going to go over that right now. It says for a given N value, a lower L value indicates a lower energy sublevel. Okay, well, let's follow here. So we go from a 1s, okay? Then we go to, let me just use commas. Then we go to a 2s, right? And then from the 2s, we go to the 2p. Then we go from the 3s to the 3p. Can anybody tell me what comes after the 3p? And I'm just following the periodic table. I'm not doing anything magic here. What comes after? What sublevel comes after 3p? 4s. Thanks, Josh, right? I go to a 4s. Who could tell me what comes after 4s? Again, I'm just following this slide. I'm going from here to here. What is this called? 3D. That's right. Okay, 3D. Okay, and then what comes after 3D? Not a trick question, guys. What comes after 3D? Great students, right? 4P. Okay, so you can see that they really follow a specific order, going from 1s to 2s to 2p to 3s to 3p to 4s. And then you think, well, shouldn't I go from 3p to 3d, or 4s to 4p? You see that they kind of switch orders right here, okay? It's kind of strange. And there's a good reason for that, okay? It says here that in general, energies of sublevels increase as the N increases and as the L increases. But what happens is, and again, this is something I'm not going to quiz you on, but if you're wondering, like, why don't they follow like the perfect order? Why is it once you get to 4s, they start to get kind of weird, okay? They go from 4s, they go from a 4s, then to a 3d, then to a 4p, then a 5s, 4d, 4p, 6s, 4f, 5d, 6p, 7s, 5f, right? Why do they do that kind of weird order? And the quick and dirty answer is this, okay? The quick and dirty answer is this, just that as the N increases, some sublevels just kind of overlap because they're so close in energy. And that's good enough for general chemistry 1. You don't need to know anything beyond that. All right, so there we go. So again, I know I keep coming back to this slide. Why? Because it's important, okay? We're going to actually use this moving forward in this class. So I'm going to try to keep track of where this is here. All right, well, let's move on to the next slide. It says here, electron configurations and orbital diagrams. So an electron configuration, which is one of the major cruxes of what we want to learn today, it says this shorthand notation consists of the principal energy level, our N value. Okay, so oops, didn't mean to do that. We have our N value. We have the letter designation of the sublevel. We have the number of electrons in the sublevel written as a superscript. So, for example, what's shown here is you have N, L, and then a number up like that. So, for example, if I had 2s, if I had a principal quantum number of 2, and let's say I had a P sublevel, I'd put P here, and let's say I had 4 electrons in there, I'd put 2p4 like that. Okay, and you're going to have to be able to do that. So let's get to it. It says here an orbital diagram consists of a box or just a line. So I'll tell you right now, let me just highlight this for you since I'm your instructor. This is what Mr. Dion will be using, okay, because Mr. Dion is not very good at drawing boxes. So it says for each orbital in a given energy level, grouped by sublevel with NL designation shown below, with an arrow representing each electron and its spin. So the whole thing about arrows, I'll just do this now instead of the next slide. It says an arrow representing each electron and its spin. So the way I like to do it is, and I'm going to go over this again, is for an orbital, sometimes you'll see a box drawn like this, okay? And then you want to put one electron, so they'll put it up like this. I like to just draw a line, and I can't even do this. I can't even put a double head and an arrow. I just put a single head like that, okay? So you're like, wow, that's a lot of time saving there, Mr. Dean. Okay, anyhow, so if we have lithium, okay, and if you're like, what is this thing here with boxes and energy and 1s? Okay, let me show you where this comes from. What's the atom we're talking about here? We're talking about a lithium. We're talking about a lithium atom. So let's go back here, okay? So lithium, maybe I'll use a black pen. So lithium is element number 3, okay? Element number 3 in the periodic table. So we're going to start here. We've got 1s and we've got 1 electron, right? Hydrogen has 1 electron. So we've got 1s, and we're going to go over here to helium, and that's got 1s as well. But remember, the s only has 1 orbital, right? And it can hold a maximum of 2 electrons. So I've got 1s, 2, like that. Now I'm down to 2s. My lithium atom is right here. So I'm going to have 2s1 like that, because I only have 3 electrons total in lithium. Look, 1, 2 plus 1. So that gives me a total of 3 electrons. So that's where that 1s2, 2s1 comes from. Let's go back here. And we said that lithium had an electron configuration of 1s2, 2s1. Now, the way that they've drawn it here is they've used a vertical orbital diagram to show that we have lowest energy orbitals or sublevels down here, lowest E, right? And then higher E up here, okay? Higher E. And a lot of times it's a convention that you draw out all the orbitals for your principal quantum number. So we have a principal quantum number of 1. There's only 1 orbital, which is an s orbital. You put the 2 electrons in it. Then you have 2, and you have a total of for a principal quantum number of 2, you can have sublevels 2s and 2p. I generally won't be drawing extra orbitals a whole heck of a lot in this chapter unless I really need to, but I'll do you one better. I don't even like to draw it out like this, okay? I have a much simpler way. I just do it like this. I say if I have lithium 1s1, 2s1, I'll say lithium, and then I'll write out my 1s orbital and then my 2s orbital like that. So in some books, they'll write out lithium and they'll put lithium and they'll put 1s and they'll put a box like this, and then 2s, put a box like this. Again, I like to just use lines, so I'll put 1 electron. The first electron by convention is always pointing up. The second electron by convention is pointing down. The first electron, again, by convention, that's your plus a half, and this is your minus a half, okay, like this. And then the third electron is in the 2s. I'm going to put it up like this. Okay, so if you're perusing the internet, and as the author of our book does, he likes to actually put the arrows up, down, up, down. So again, in the vertical orbital diagram, we have the energy going up in this direction, And I like to use the horizontal representation where energy is going up or going or increasing, going from left to right. Okay, so if you're like, oh, I'm going to need more practice on this, good. Okay, but before we do that, and we will do some practice today for sure, I want to go over a couple of concepts with you, 3 concepts to be exact, that you need to understand before we can get into the whole, trying of the problems. Okay, so it says here, building orbital diagrams, the Aufbau principle and the Pauli exclusion principle. It says the Aufbau principle is this. Electrons are always placed in the lowest energy sublevel available. So whatever the lowest sublevel we got, that's where we're going to put our electrons. We don't start putting electrons in higher energy sublevels until we filled up the lowest energy sublevels. The next rule, it says the Pauli exclusion principle states that each orbital may contain a maximum of 2 electrons, but they've got to have opposite spins. So if I have 1s2, one's got to be up, one's going to be down. The next one is my favorite rule, and it applies once you get to the p orbitals, because there are 3 types of p orbitals. And if you're like, well, how do you know there's 3 types of p orbitals, Mr. Dion? Well, remember, I told you that when you have L is equal to 0, 1, 2, or 3, this is an s orbital, this is a p, this is a d, this is an f. So when I have p is equal to, L is equal to 1, that's a p orbital. What are my possible values of ml when I have 1? Is my angular momentum quantum number. I have -1, 0, and +1. And you remember from last Friday, I told you that the number of ml values you have, that means the number of orbitals that you have. So you have 3 orbitals for a p, right? For p orbitals, for p, there's 3 types of orbitals, I should say. Anyhow, so Hund's rule is this. It says here that it specifies that when orbitals of equal energy are available, the lowest energy electron configuration has the maximum number of unpaired electrons with parallel spins. Okay, so if I have nitrogen, which has an atomic number of 7, let me just write out the orbitals like this. If I have 1s like this, and I have a 2s, and then for 2p, we said there's 3 types of orbitals. They're all equal in energy. Okay, so we have 7 electrons. So I'm going to start with 1s because that's lowest energy. So I have 1, 2. Now I've got 7 electrons in here, and I've only used up 2 of them. So let's keep going. In my 2s orbital, which is my next lowest energy, I'm going to put 1, 2, like that. Okay, just like that. So now I've accounted for 4. I've got 3 more electrons. So here's why I have a picture of people on the bus, because Hund's rule, sometimes I call it the bus rule. Okay, so what happens if you get on the bus, right, and there's somebody sitting in a seat? Okay, I have 3 more electrons, now I've got 2 left to put in. But if you step on a bus and there's 2 empty seats and then there's 1 person sitting alone, would you go sit next to that person? If it's somebody you don't know, I'll just ask my students, would anybody do that?
Nah.
Okay, good. No, me neither, man. No way. Okay. It makes you look like you're, somebody said, goodness, no. It makes you look like you're some kind of, yeah. Good one, Amanda. Anyhow, it just makes you look like you're some kind of nut, if there's a beautiful empty seat. So you're going to go to the next seat. Okay. So Amanda steps on the bus and she said, well, there's 2 seats with each have 1 person, but there's still an empty seat. And I'm the last electron stepping on the bus, right, Amanda? So she's going to sit right there. And that's what Hund's rule is. Let's say we had oxygen. Okay, so oxygen has 8 electrons, and it's 1s2, 2s2, 2p4. And we'll get to that in a second. So we have 1s, 2s, and the 2p. So 1s2, 2s, and then 2p. So we have 1, 2, 3, 4, 5, 6, 7. Once you step on the bus in your oxygen and you got another electron to go, you're like, dang it, I guess I have to sit next to somebody I don't know. And so that 4th electron in the p orbital is going to go to the 1st orbital, okay? Don't ever make the mistake of being like, I'll just sit in the middle. No. You start down here and then you work your way up, okay? Give me a thumbs up if you follow me on that. Now we're going to get to the good stuff. This is what you showed up for on a Monday morning, right, Alexis? This is what you came here for, okay? Bruce is like, take me to the good stuff. Take me to the writing out electron configurations. All right, well, let's give it the old shot here. Okay. All righty, well, let's give it a shot here. So it says, give the complete electron configuration of each element. So we're going to start with beryllium. It has a total of 4 electrons. And just to help us out, I'm going to back up all the way back here, all the way to this periodic table, and we're going to talk about beryllium. So just give me a second while I do some erasage, as we say in French. Kidding, kidding. Anyhow, so beryllium, we said, had 4 electrons. So where do I start? I always start here. 1s, 1. 1s, 2. So we've got that, 1s, 2, because we can have a maximum of 2 electrons in an s orbital. Remember, beryllium is found right here in the periodic table. So then I go over here to 2s, 1, 2s, 2. So the electron configuration is 1s2, 2s2. Let's take that to the bank and put it back here. So we've got 1s2, 2s2. Let's give nitrogen a shot. So nitrogen has a total of 7 electrons. Didn't we already do that on the last slide? So I'm going to write it out here. It's 1s2, 2s2, 2p3, like that. Let's try something tougher. Let's go to sodium, which has a total of 11 electrons. Let's go back here. This is why you got to have a periodic table, my friends, because you need to know where sodium is in the periodic table, and sodium is right here. This is where you find Na. So we've already gotten thus far, right, to the 4th electron. So we go from 1s2, then we go to 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So let's write that out, because remember, a p orbital can hold, p has 3 different orbitals. They can each hold a maximum of 2 electrons. So that's 2p6. And then ding, 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 ding. Here I am at sodium. Okay. So sodium has 3s what? 3s1. 3s1. Give me a thumbs up if you follow me on this. We're just walking through the periodic table, my friends. Cha? Yeah, good. Last spring when I taught this class, I'd always say to the students, cha? All right. Cha. Where were we? Sodium. So sodium is 1s2, 2s2, 2p6, 3. Oops, getting ahead of myself. 3s1, like that. If you're like, hey, Mr. Dion, do all electron configurations always start the same way? With if you had more than 2 electrons, 2s2, or 1s2, then 2s2, and then so on and so forth? The answer is yes. They're the same order every time. There's only a couple of exceptions. Let's give chlorine a try. So chlorine is element number 17, like that. It's got 17 electrons. Again, you're going to need a periodic table. Wrong way. Chlorine is right. Huh? Okay, so this is chlorine, like that. Okay, so I'm going to go from 3s1 to 3s2 over 3p1, 3p2, 3p3, 3p4, 3p5. So I go to 3p5, like that. Okay, so we got chlorine figured out. Oops, son of a gun. Let's put that in here. Throwing it in. You can see I was really excited to do today's class. Get me to chemistry. 3p5, like that. You guys want to do a funky one? Okay, let me show you a crazy one. Okay, silver. Silver has 47 electrons. Let's use blue. Okay, 47 electrons. Back to the periodic table. Silver. Are you going to talk about that? Yeah, we're going to talk about that. So silver is right here. Okay, so Ag. Okay, as my students always like to remind me, that chemistry is about learning a lot of rules and then learning the exceptions to those rules. So are you ready for a cool exception? Okay, let me teach you a really interesting exception, and it involves silver. Obviously, you can tell it's where I'm going. So for chlorine, we had, where were we? We had 3p5, 3p6. Then we go over here, 4s1. So 3p. Oh, again, Mr. Dion, you're losing it. Did I make a mistake on this one by accident? Because there's no such thing as 3s5. Should have said 3s2, 3p5 for the previous one. Sorry, you guys. Anyhow, no, we're not talking about charges, Gino. We're just talking about the elements, okay? We'll get to ions probably next class. Okay, we're not talking about ions at all. We're not talking about compounds. We're just talking about electron bookkeeping for elements in the periodic table. All right, good. So we got 4s1, 4s2. Look at this. It drops down. Remember I told you that as you get to higher sublevels, sometimes they take on kind of interesting orders. Well, I can tell you that for the D block, you always drop down one. So you have period 1, 2, 3, 4, 5, 6, and 7. So for the D block, you always take n and then you subtract 1, right? N subtract 1, n subtract 1, n subtract 1, right? 4 minus 1 is 3. 5 minus 1 is 4. 6 minus 1 is 5. 7 minus 1 is 6. And for the lanthanides and actinides, you do n minus 2. So n minus 2. So the lanthanides and actinides actually get squozen. Is that a word? Squozen? I don't know. They get put right here. Okay, so if you have 6 minus 2, right? 6 minus 2 gives you 4, and 7 minus 2 gives you 5. So if you've ever wondered where those come from, anyhow, there we go. So we have 4s2. We still haven't gotten even close to our silver yet, have we? We got 4s2, then we get 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. So let's write this out. So 3p6, then we have 4s2, then we have 3d10. Still not there. It's square. Okay, good. Anyhow, then we move on to 4p1, 4p2, 4p3, 4p4, 4p5, 4p6, 4p6, 5s1, 5s2. So let's put that down. 5s2, 41, 42, 43, 44, 4d5, 4d6, 4d7, 4d8, 4d9. So 4d9. So instead of me rewriting this, can I copy and paste that, you think? Give it the old college try here. Copy. Let's go back. Let's go back here. Come on, baby. Oh, yeah, there we go. Okay, it's not perfect. Kind of pretty it up here. My 3p6 is a little funky looking. All right. So this is an exception. It's silver. It's an interesting exception. So you have 5s2 and 49. And if you're like, do I have to memorize this exception? Oh, yeah. The ACS loves these electron configuration exceptions. Okay. So you have 5s2, 49. If you were to take nursing level chemistry, which is chemistry, which is at UCCS, it's chemistry 1201. They would accept that, but in this class, we won't do it that way. We do it like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. Maybe I should use a different color here. We're going to use 5s1 and 4d10, okay? And if you're wondering, like, why do they do that, okay? It's because there's some stability that's gained by having orbitals either half full or completely full. And if you look at this one, okay, this is full, and this is not full or half full. Whereas here, this is half full, and this is full. So it's actually more stable, okay? So for chemistry, what's our class called? Chemistry 1401. Chemistry 1401. Okay, 1401, like that. And the elements that you see this exception in are chromium and copper, molybdenum and silver, and you do not see it in tungsten, not seen in tungsten, and it's also seen in gold. Okay, so if you have a periodic table, I know a lot of my students like to buy these periodic tables that have information on them, like electron configurations. Well, that's why you have that interesting kind of electron configuration. Give me a thumbs up if you're like even 80% of the way with me on electron configuration, electron bookkeeping. Like, I just need to sit down with some practice, you know, and I'm going to nail it after that. Just give me a few minutes. All right, it's MO, molybdenum. Molybdenum. There's no MJ in the periodic table. He was a singer, okay, with a glove. All right, anyhow, it says here correlating quantum numbers in orbital diagrams. It says use the orbital diagram for fluorine to write sets of quantum numbers for the 3rd and 8th electrons of the fluorine atom. Well, let's start out by writing the electron configuration. I'm going to go a little bit faster here. Fluorine has a total of 9 electrons. So that means we have 1s2, 2s2, and 2p5, like that. Okay, so that's just to kind of get me going. So I have 1s orbital, then I have 2s orbital, and then I have 3 2p orbitals like this. I'm going to fill them up. 1, 2, 1, 2, and then 1, 2, 3, 4, 5. So it says here the 3rd and the 8th electron. So let me erase all these in and I'll do it with this. Okay, so let's fill them up. We've got 1, 2, 3. So we're going to write a set of quantum numbers for this fellow right here. And why don't I write it in green? That way we can bookkeep it. And we're going to write them out like this. We're going to have our N, our L, our ML, and our MS. Okay, so for this 3rd electron, right, this is the 3rd one right here. So our N is the principal quantum number, which is 2. Remember, when we have L is equal to 0, 1, 2, or 3, we have S, P, D, and F. And since we have a 2s, that means that our L is equal to 0. When L is equal to 0, ML can only equal 0, and our MS, since it's pointing up, since the arrow is going up like this, that means that we're going to call it plus a half. So plus 1/2 like that. Okay. Now it says, so that was the 3rd. Now we're going to do it for the 8th electron. So let's go back. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then there's a total of 9, so I'll just put the 9th one in there. So now we're going to do it for this guy, for the 8th one right here. So let's do that. I forgot to close my bracket here, didn't I? Okay, so for the 8th one, we have our N is equal to 2. We have our sublevel is P, and so that means that our L is going to be equal to 1. So let's put that in. Now, something that I haven't pointed out is that when you have the orbitals, the ML values go like this. So if I have an L equal to 1, my ML values are going to be -1. Oops, they're going to be -1, 0, and +1. This represents the 3 orbitals. And so since it's in the first one, it's going to be -1, like that. And then the last one says +1. The arrow is pointing up, so that's going to be +1/2, like that. Give me a thumbs up if you follow me on writing out these quantum numbers. All right, cool. Well, that covers a lot of what you need to know how to do today. That covers a major part of it, okay? Let me just show you this picture here. I find that our textbook has all kinds of like interesting pictures in it. I'll just use the word interesting. She has interesting ways of thinking about things. Anyhow, it makes sense, I guess. So what she's doing here in this figure is depicting orbital occupancy for the first 10 elements. So now we're going to step back a little bit. We're going to slow down like this, slow down a little bit. Did I put +1/2 when it was supposed to be -1/2? Yeah, should be -1/2. -1/2 because it's pointing down. So down, therefore -1/2. Good. Thanks for pointing that out. All right, where was I? I was here. I mean, I don't want to spend too much time in a picture. Sometimes I just get lost in these things and just like to just gander at it for fun. But the idea here is that you have a 1s orbital. Remember that an s orbital is a sphere, and that a p orbital is Gage called it the peanut. P is for peanut. Anyhow. So first we start with 1, period 1, right? We have 1s1. And then when she has 1s2, the more electrons, so it's darker, so this is light. This is a thing that's in our textbook, okay? Then it's darker here, okay? So then she goes to a 2s orbital, and 2s is just going to be a bigger sphere. At first it's kind of light, then it's kind of darker here, you can see. Then she puts in the p orbitals, right? And when you have a p orbital, right, you can have, you can actually have a px, py, and pz. It can have 3 orientations, px, we can call them however we want, py, and then the pz is in the other plane, anyhow, like that. So here you see this one is kind of half shaded. Then she puts the next one, right, because you go into the next orbital because of Hund's rule. Then when you have 3p electrons, all three of them have 1 electron in it. Then you have to start filling them up, going back to this one here. So you shade this in. Then you go to the next one and you shade all of them in, right? And then you go and you fill them all up like that. If that helps you, like as a visual representation, no problem whatsoever. It's cool. Let's talk about some other things here. Because if you're thinking like, hey, Mr. Dion, what if I have to write out the electron configuration of Einsteinium or Californium? You got 98 or 100, 99 electrons or something. Would I have to do that? Well, you can, for sure. But there's faster ways of doing it. And one is a partial orbital diagram. That only shows the highest energy sublevels that are being filled. Okay, so we just leave everything out. I don't use these a whole lot. Okay, I don't use them a ton. I like to use these though quite a bit, which is a condensed electron configuration. In fact, if you look at most periodic tables that include electron configuration, they always include a condensed electron configuration. And what it does is it says it has the element symbol of the previous noble gas in square brackets. So if you had aluminum, right? So let's just practice aluminum, which is right here, which is 1s2, 2s2, 2p6, 3s2, 3p1, right? You have 1, 2, 3, 4, plus 6 is 10, 12, 13. So you have all 13 electrons accounted for in there. But instead of writing all of this out here, the 1s2, the 2s2, and the 2p6, they shorten that to just neon with square brackets like this. So you just write neon in square brackets like that. So if we back up, if you're like, where does that come from, Mr. Dion? Well, actually point to the periodic table on the wall if we were in the room. But the element that we were talking about is aluminum. Oh, jeepers. There's a lot of scribbling on here. I forgive me for that. But aluminum is found, I'll highlight it for you in yellow. It's found right here. Okay, so, and if I fill in the noble gases, here I have helium, here I have neon, argon, krypton, xenon, like that. So what's the noble? So if this is aluminum right here, what's the noble gas that precedes it? Not the closest noble gas, the noble gas that comes before it. You go backwards, backwards, and then here I'm over at neon like that. Okay, good, thanks, perfect, you guys. So it's neon, and neon has a total of what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And so if you just write that neon in those square brackets, that accounts for those first 10 electrons. And so where the heck was I? Sorry, I'm doing a lot of jumping around today. Okay, and so that would be a condensed configuration. We could even back up here to one of these examples, one of these ones here. So let's say we were going to do the same thing for chlorine. What's the noble gas that precedes chlorine? Not a trick question. Precedes means comes before it. I think my students put, no, maybe they didn't. Yeah, it's neon, exactly. So for chlorine, you do the exact same thing, right? These electrons here could be represented by neon like this, and then you would write 3s2, 3p5, okay? And if, this is not something that's in my slides, if you're wondering, like, what's the significance? Like, why would I want to do that? Just to save time and to prevent my wrist from getting sore or me running out of pencil lead or whatever? Well, the reason why is because oftentimes it's nice to focus on outer electrons, because usually, and especially in a lot of chemistry that we look at in Chemistry 1401, the reactivity is going to come from the electron configuration or the electrons that are the farthest away from the core, okay? So something kind of interesting there. Well, with that in mind, let's draw the shorthand for these ones. I don't want to spend a ton of time on this, okay? Because I've scribbled so much over my periodic table already. So I'm going to count on you. I'm going to count on you to have a periodic table with you right now, okay? So I don't have to rifle back. Before I move on, I just want to remind you of a couple things, okay? And I'm going to delete this in a second. But I want to remind you of a couple things, is that when you are drawing orbital box diagrams, or as I call them, orbital line diagrams, when n is equal to 0, 1, 2, and 3, if it's 0, we have an s orbital. There's only one type of s orbital, right? So you would represent that as a single line like that. If we have a p orbital, there's 3 types of p orbitals. So when I have a p orbital, I have 3 lines like that, okay? If I have a principal quantum number of, sorry, did I write n when I should have written L? There we go. All right, so when I have an L equal to 2, I have a d orbital. And when I have a d orbital, remember, when L is equal to 2, ML can be -2, -1, 0, +1, +2. That's a total of what? 1, 2, 3, 4, 5 orbitals. So when you have D, you have a total of 1, 2, 3, 4, 5 orbitals. And then when you have F, okay, when your L is equal to 3, you have F orbitals. How many types of F orbitals are there? And you're like, well, I saw 7 last week. Yeah, that's right, because ML can be equal to -3, -2, -1, 0, +1, +2, and +3. So looky, 1, 2, 3, 4, 5, 6, 7. So when we have F orbitals and we write out the orbitals, we say 1, 2, 3, 4, 5, 6, 7. Okay, so that's a little more background before we get cooking here. Okay, you can take that to the bank and cash it in. What time does this class end? Noon? I forget. Is it 10:50 or 10:40? Like 3 p.m. Yeah. I'm with you, Don. I have it written down here on my wall. I could just lift up my eyes. Yeah, it's 10:40. Yeah. Okay, so let's go back to nitrogen. Now, we did nitrogen earlier, and we said that nitrogen had an electron configuration of 1s2, 2s2, 2p3. So what's the noble gas that precedes nitrogen? What noble gas comes before nitrogen? Not a trick question. This guy doesn't like, it's helium. Exactly. And so the shorthand would be, so now we're going to do the condensed, or shorthand would be helium 2s2, 2p3. Okay, for sulfur, if you write it the complete electron configuration, sulfur has a total of 16 electrons. So 16 electrons, so it goes 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4. So 3p4. These are the core electrons here. Okay, those 10 electrons. And the noble gas that precedes sulfur is neon. And so we can write neon in square brackets like this. And then we'll write 3s2, 3p5. Titanium has a total of 22 electrons. So 22 electrons. Can anybody tell me what the noble gas is that precedes titanium? Again, not a trick question. Mr. Dion does not like trick questions. Yeah, thanks, Ashlyn. It's argon. Exactly. Good. Alexis, Lindsay, whole gang. Cruz, bada boom, bada bang. All right, everybody says argon. Could you figure it out just by starting with argon? Could anybody tell me what should come after argon, or even just give me a clue? After argon, what would I write next? And I know this is difficult, maybe challenging to communicate via the chat, but just give me a heads up. Yeah, 4s. It's 4s2. Yeah, I see 4s2. And then I have to go into the 3D. And then I have to go 1, 2, because the first transition metal is scandium, and the next one is titanium. And so I have 3D2 like that. All right, and if you want to write out the whole thing, you'd say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, like that. Okay, and we covered all of this, okay, with that, with this symbol here, right? Just like we did here, and just like we did here. Okay, try the next one. SN. Sorry, that's tin. Okay, so tin is element number 50 on the periodic table. Tin's in the same family as carbon, so it's kind of got a soft spot in my heart. Anyhow, so 50 electrons. We write out the whole thing. Who could tell me, you know what, maybe I'm going too slow. What's the noble gas that precedes tin? Again, not a trick question. Yeah, I think you guys are probably going faster than me. Yeah, it's krypton. Yeah, so krypton. And then what comes after krypton? Then you're in the 5th period. Then you have 5s2. Then you have to go all the way through the 4ds, right? And there's a total of 10 electrons possible in 4d, 4d10, and then you have to go to 5p, and then you count over 1, 2. So 5p2, like that. Okay. Give me a thumbs up if you follow me on this. If you understand this, my friend, you are cooking with gas. Okay? You are in a good spot. And you're already in a good spot because you signed up for chemistry. But yes, you're in a good spot if you follow me on that. All righty. Well, let's move on. You know, we can't just yammer on and memorize rules and everything without talking a little bit about what's so great about this. Like, what's so important about this? Well, let me show you something that you're probably all already aware of because I talked about it a little bit in class. But remember that I told you the elements that are in the same group, like say, for instance, the alkali metals will react similarly, right? The alkaline earth, they react similarly. The halogens react similarly. The noble gases are unreactive, right? Well, it says here the elements in the same group of the periodic table have not only similar chemical behavior, okay, under electron configuration. Did you notice that? Okay, and it says here the similar outer electron configurations correlate with similar chemical behavior. Look at this. Did you notice that all the elements in group 1A would always somehow, whether it's lithium, sodium, potassium, rubidium, cesium, francium, they all end up with NS1. Okay, so a seasoned chemist, she might look at that and say, well, you know, I see NS1 in my electron configuration. It's going to have this kind of reactivity, right? A seasoned chemist might look at this electron configuration, say NS2, that's from group 2A. You know, it's going to have this kind of reactivity. Look at this. In the noble gases, they all end up with this, where you have NS2, NP6, right? What does that mean? That's a total of 8 electrons in your highest principal quantum number. Okay, doesn't matter what noble gas you're talking about. And if you've ever heard of the octet rule, we'll talk about it later on in this class. But that's where the octet rule comes from. It's because both in the halogens, right? This is the halogens. Both the S is full and the P is full. And remember, I told you there was some inherent stability about having orbitals half full or completely full. Kind of cool, huh? Kind of cool. You can even write that here. You can put, if you really have an inquiry mind, both full. No vacancy, right? Okay. Who's enjoying this so far? Who's like, I think I can get the hang of this. I think I might survive electron configuration. Yeah. All right, me. All right, I'll take it. This is simpler than, you know, quantum mechanics wise in the Schrodinger equation. Yeah, for sure, for sure. And you know what? I don't want to just, so let me just stop there for a second. I'm not just talking to the students who are giving me thumbs up and saying that they follow along. Well, even if you're with me half of the way, well, you're like, I think I have it. I kind of understand what you're saying, but maybe not 100%. What are you going to have to do? You're going to have to try some practice. You know, get the book out, actually look at it, double check it, look at my lecture slides, go back to the video, and you're going to have to, you know, try to figure it out. That's part of what being a college student is. Okay, it says here partial, I mean, this slide is just for FYI, partial orbital diagrams for an electron configurations for the elements of period 3. So we go from sodium all the way to argon. So look, we always follow what? The Aufbau principle, the Pauli exclusion principle, and Hund's rule. Those are the 3 rules as we fill up these orbital diagrams, right? You start with the lowest energy level, you get that all filled up, then you move here. Then according to Hund's rule, the bus rule, you go to the next seat, then you go to the next seat. It's only until all 3 of those seats are filled up that you're like, darn it, I gotta go into a seat and sit next to some stranger, you know, that I don't want to or something. Okay, anyhow, so it follows along, and anyhow, I mean, we've gone over this in quite a bit of detail, so this is a lot of FYI. Here's those exceptions that I mentioned before. The one that we did was silver, but if you look at the group in the periodic table that has chromium in it, and I'll just rewrite them here, you have chromium, and then you have molybdenum below it, and then you have tungsten below that. If you look at copper, what comes below copper is silver, and then what's below silver is gold, okay? So all the ones that are highlighted in red actually follow this exception, okay? So these exceptions right here. And again, we did silver. So if you look at chromium, if you were to write out the electron configuration, you'd have this. You'd have this. Argon 4s2 3d4. Now, what you do is you take one of those s electrons and you put it in the d, so that you end up with both of these, both 1/2 filled. Okay, that's what's going on right here. Okay, and with the example of copper, which is similar to that of silver, okay, you would end up with 4s2 3d9, but we take one of these electrons and we plop it in here so that we end up with this. Okay, and so the 4s orbital is half filled, and the d orbital is full, completely full. All right, this rule again does not apply to tungsten. Okay, you can even put in here rule does not apply. Okay, the rule doesn't matter here. The energy levels of the orbitals are close to each other. There's a gain in stability by producing half-filled or a filled shell when you can. I'm tired today. This shows you the fourth period. But remember that when we have the fourth period, after we go through 4s1, 4s2, then we get to what? The transition metals. And remember that for the transition metals, from scandium all the way to, well, I'm not highlighting them, from scandium all the way down to zinc, you're adding to a 3D orbital, 3D1, 3D2, 3D3, 3D5, right? Because of the rule here, 3D5, 3D6, 3D7, 3D8, 3D10, 3D10. Right, why? Because a d orbital has how many? 1, 2, 3, 4, 5, okay? And we've gone over that in dirty detail. Then, once you get back to the p block, you go back up to a principal quantum number of 4, okay? All right, that's that. I'm sure that somebody who's hearing my voice right now has one of these periodic tables that has all of the electron configurations on it for every element in the periodic table. These are really handy. You know, these can be really, really handy when you're studying. You can see that all that's on here is the partial or the condensed, or sorry, I should say the partial ground state electron configurations. Before we end here, I want to just put one bug in your ear, or another bug in your ear, I should say, is what does ground state mean? Ground state means it's not an excited state. So when you're grounded, you're not excited, okay? So ground state, all that means is that the Aufbau principle is obeyed, and all of the electrons are in the lowest possible energy sublevel, okay? So that means you don't skip, you don't put a 1s electron into a 2s or something like that. And if you're wondering, can that happen? Yes. We will see that later on, not until around November, actually. In fact, I looked at the schedule last night. We'll learn, and if anybody here has taken AP chemistry before, is anybody that's hearing my voice, has anybody ever heard of the concept of hybridization in electron configuration or hybrid orbitals?
Yes.
Okay, so if you've heard of hybridization in hybrid orbitals, well then, that's when we would deal with electron configurations that aren't the ground state. I put a lot of slides in here to try to help you out. This is another one here that just shows you the order in which the orbitals are filled in the periodic table. You can take it directly from the periodic table. This is the way that I do it, okay? 100% of the time, Mr. Dion always goes straight from the periodic table. There is, and you're like, is there another way? Yeah, there's another way. And I don't have my book here, and I don't have my book open, but there's another figure in the book that shows you another way to order it. I don't teach that way because I find students always have a periodic table with them. I always give you a periodic table. You know what? We got 2 minutes. Let's try one question, and then you guys are probably eager to move on with life for the rest of the day anyway. It says here, which element has this electron configuration? I'll just throw that out there to my students. See if anybody can nail this one. Which element has this configuration?
It's E.
It's E, yeah, cobalt. Right? It's going to be cobalt because cobalt has. Oops, I didn't mean to do that. I'm doing a lot of weird things today. Cobalt has a total of how many electrons? It's got a total of 27 electrons. So we go 1s2, 2s2, 2p, 2p6, 3s2, 3p6, 4s2. And then when we go to 3D, cobalt is found 1, 2, 3, 4, 5, 6, 7 elements over. So it's 3d7. And the noble gas that precedes cobalt is argon. And so all of this spinach here can be represented by argon brackets, and then we just have 4s2, 3d7. Like that. All right, there we go. All that brings. We answered that question.